Let's use partial fractions to integrate 5 divided by x to the third minus x squared plus 9x minus 9 dx. The first thing we need to do is make sure our denominator is of higher degree than our numerator. And in this case, we have a third degree polynomial in our denominator and a 0 degree polynomial in our numerator. And if you didn't know, a constant is a 0 degree polynomial. So we can use partial fractions, and the first step to partial fractions is factoring our denominator. And that will give us the integral of 5 divided by x minus 1 times x squared plus 9 dx. So taking a look at our denominator, we have an x squared plus 9, which can't be factored any further, giving us case 3, a denominator which contains a distinct quadratic factor. Quadratic because x squared plus 9 is a second degree polynomial, and distinct because this factor has multiplicity 1. We also have a distinct linear factor of x minus 1. So when we rewrite this integral, we'll still have some constant a divided by our linear factor x minus 1, and we'll create a term for our quadratic factor of x squared plus 9. But whenever we create a term for one of our factors, the numerator has to be 1 degree lower than the factor associated with it. So because x squared plus 9 is quadratic, so a second degree polynomial, the numerator has to be a first degree polynomial. And the general form of a first degree polynomial is some constant, which we'll call b, times x, plus some constant, which we'll call c. We can use this information to create an equation to solve for a, b, and c. Because if these integrals are equal, their integrands are also equal. So that will give us 5 divided by x minus 1 times x squared plus 9 equals a divided by x minus 1 plus bx plus c divided by x squared plus 9. Now we can simplify this by multiplying both sides by our denominator here. So if we multiply the left by our denominator, we'll just have 5. And if we multiply this fraction by this denominator, x minus 1 will cancel, giving us a times x squared plus 9. And if we multiply this fraction by this denominator, x squared plus 9 will cancel, giving us bx plus c times x minus 1. Now we can choose values for x that allow us to cancel some of our constants so we can solve for others. Sometimes it's useful to multiply this out first so that we can group terms. So we'll have a times some polynomial plus b times some polynomial plus c times some polynomial. But in this case, we have an obvious choice for x that will allow us to cancel b and c to solve for a right away, and that's x equals 1. Because this becomes 1 minus 1, which equals 0, canceling out b and c. So if we let x equal 1, the left side stays the same, and the right side becomes a times 1 squared plus 9 plus 0. Then solving for a, we get a equals 1/2. And we can substitute this back into our equation, giving us 5 equals 1/2 times x squared plus 9 plus bx plus c times x minus 1. And now we just have b and c to solve for. We'll notice that b is being multiplied by x and c isn't. So if we just let x equal 0, it will cancel out b, leaving us with just c to solve for. So if x equals 0, the left side stays the same, which is 5. The right side becomes 1/2 times 9 plus c times -1. And solving for c gives us c equals -1/2. And we can substitute that back into our equation, giving us 5 equals 1/2 times x squared plus 9 plus bx minus 1/2 times x minus 1. And there's a few different ways we could go about this. We could let x equal anything that won't cancel b out, But we can also just see that if we manipulate this enough algebraically, which I'll leave the viewer to do, all of our x's will cancel anyway, leaving us with b equals negative 1/2. Substituting these values back into our integral gives us the integral of 1/2 divided by x minus 1 plus negative 1/2 x minus 1/2 divided by x squared plus 9 dx. And we can factor out a 1/2 and simplify this, giving us 1/2 times the integral of 1 divided by x minus 1 minus x plus 1 divided by x squared plus 9 dx. We can rewrite this as a sum of integrals, giving us 1/2, open brackets, the integral of 1 divided by x minus 1 dx minus the integral of x plus 1 divided by x squared plus 9 dx, close brackets. To make integration easier, we'll actually break up this integral into two separate integrals, and we'll distribute this negative sign when we do that. And that will give us 1/2, open brackets, the integral of 1 divided by x minus 1 dx minus the integral of x divided by x squared plus 9 dx minus the integral of 1 divided by x squared plus 9 dx, close brackets. Now we can integrate, and that will give us 1/2, open brackets. This first integral will be a u substitution where u equals x minus 1, giving us ln, absolute value of x minus 1, minus. This second integral will be a u substitution where u equals x squared plus 9, giving us 1/2 ln absolute value of x squared plus 9 minus. And this third integral can be a bit challenging, but through some algebraic manipulation, we actually can use a u substitution. So to give you a few clues on how to get started, try first factoring a 9 out of this denominator. So your new integrand will be 1 divided by 9 times x squared divided by 9 plus 1. And you'll also need to know that a common integral is the integral of 1 divided by x squared plus 1 is equal to the inverse tangent of x. And using these two things, you'll find that u equals x divided by 3. So integrating gives us 1/3 inverse tangent of x divided by 3. We can close brackets and add plus c for our constant of integration.